We're still solving partial differential equation boundary value problems. We're going to run into the same kind of eigenvalue problems fairly often in solving these boundary value problems for partial differential equations. Here would be the equation, and here's 4 different permutations of boundary conditions for this equation, just using the function and its derivative at each end of a finite interval. We've already done this first case where the function is just 0 at both ends of little x. So I'm not going to go through that. Again, you get 3 cases. You know, all these guys, the general solution to this equation is, well, it depends on what lambda is. It's either this guy with the hyperbolic tangent stuff. It's this linear thing if lambda equals 0, and it's this mixture of cosines and sines if lambda is positive. I'm not going to go through this again, but for this case, you'll get these eigenvalues and these eigenfunctions. So the eigenfunctions are just signs and a bunch of, ends, a bunch of positive integers. Let's do the next one. If the derivative is 0 at both ends, you'll still reject the lambda less than 0 case, but you don't reject the lambda equals 0 case. Let's see. When lambda equals 0, here's the general solution. Its derivative is just b, so that's 0. And actually, it's b at both ends. No matter what x is, the derivative is 0. So we don't have to take the trivial solution. It's just a constant. So that is one eigenvalue. Just some constant. We'll just set it to 1 here, and we'll accept that. So that's a case where lambda equals 0 is not rejected. And then for the positive cases, let's go through that. Here's the general solution. Prime will be A alpha sine, B alpha cosine. So it'll be B alpha, actually there should be an alpha there. That equals 0, but alpha isn't equal to 0, so B must be 0. That leaves cosines. And what about the other guy? When it's the cosine, the derivative is A alpha sine alpha L, evaluated in L. And that equals 0. And we know where that equals 0. It equals 0 where alpha L equals n pi. So we get some more eigenvalues and eigenfunctions. The cosine function now. Because when b was 0, because of this initial condition, boundary condition, you're left with this part. So in this case, we get cosines. Cases C and D, I'm just going to leave here. You ought to go through them once. And by the way, in case A, we can expand a function using these eigenvalues. It will be the Fourier sine series. When it's these eigenfunctions, we can expand it using Fourier cosine series. These last 2 cases, you get things that almost look like Fourier sine or cosine series, but not quite. If you go back to where we talked about orthogonal expansions, you could come up with your own Fourier series for these. Maybe you could call them the Fourier-Hoven series or something, or name them after yourself. If you go back to orthogonal expansions, you could expand a function using these eigenfunctions from these last two cases. Anyway, if you go through all those four cases, we always reject the negative lambda case. We accept the lambda exactly equal to 0 only in this case B here. The first two cases, A and B, yield a sine and cosine series, the Fourier sine and cosine series. These latter two cases, you would have to do an orthogonal expansion calculation. Anyway, let's only go through these once and then put them on a formula sheet, basically, so we don't have to keep redoing the same eigenvalue problem. Now, with that in our hip pocket, let's get to the next boundary value problem. Classic one, the wave equation, or the vibrating string. Here's the deal with the vibrating string. It's assumed that there's no motion of the spring in the x direction. X direction is this horizontal direction of the spring. The u itself is the vertical displacement of the string from 0. At least for now, we'll assume the string is attached at a height of 0 at each end. So we're assuming, no motion in the x direction. So this string has the same density everywhere and the same mass per distance along x. Anyway, if you did all that and kind of derived the physics of it, you would get this partial differential equation, where x is between 0 and L. We're only worried in time from time 0 and up. These boundary conditions correspond to it's connected firmly at each end. And then this boundary condition, our initial condition at time 0, says the position is some given function. This says this vertical velocity of the spring is some function of x at time 0. So we have two initial conditions, initial displacement and initial velocity. So let's go through solving it the way we did before. Product method, separation of variables. This equation will become, let's see, a squared x double prime t. The right side becomes x t double prime. These boundary conditions, we can split them up like we did before. This will be x at time 0 and t for all time. For that to be 0, x at time 0, or x, x equals 0, little x equals 0, and at the other end it's 0. That leads to, let's see, well, this equation here, when we separate variables, leads to this. We'll divide through by a squared t, I guess, xt. And we end up with this, all x on one side, all t on the other. For them to be equal, we set them equal to the same separating constant. I'll pick minus lambda so that I get this convenient equation with x. And we have those boundary conditions. So we have everything we need to solve the x equation. In fact, it's case A that I just went through. So we already have its eigenvalues and eigenfunctions. I'm not going to go through that eigenvalue problem again. Then for the t equation, we have to use the same eigenvalues. Here was the t equation. Now we know what the lambdas are. They're the alphas. So we have, here's the equation for t, and we know the general solution to that. You know, this is a positive number, so it's this mixture of cosines and sines. So we have the x functions and the t functions. We put them together. Infinite number of solutions that look like this. So the general solution is a linear combination or an infinite sum of these infinite solutions. So here is general solution before we apply the initial conditions. This satisfies the partial differential equation, and it also satisfies these boundary conditions. We're still left with these initial conditions. We're going to need this guy's derivative, so let's go ahead and take it here. I'm not going to go through that, but here's the derivative of the general solution. And we said Q, when time equals 0, what is Q when time equals 0? Sine is 0, cosine is just 1, so we just have a sub n sine. There is U times 0. That's a function of x. And we can expand this f of x in a sine series so that it matches this. Then we match coefficients. This a sub n must be the little b sub n's from the sine series. We had a formula for that. So the a sub n. Let's do the derivative at times. Here's the derivative. Times 0, this sine is 0. Cosine is 1, so we're just left with this part times the sine. That. And that equals that initial velocity of the string. We can expand this function, g of x, in its own sine series. It's a different sine series than this guy. So now when we match coefficients, we're matching everything in front of the sine on this side to everything in front of the sine on this side. We want this b sub n pi a over L to equal the little b sub n's. Fourier sine series, we get a formula for b sub n's. So now we know the big b sub n's. Let's just summarize it all. This is the solution to the wave equation, the way it was posed above. Here's the general solution. Here's the way to get the A's and B's. If the Fx is 0, if the initial displacement is 0 and all you have is initial velocity, all these A's become 0. On the other hand, if there is no initial velocity, say you just pull the string up in the middle, initial displacement, and then let it go, the g of x would be 0, which means all the b's are 0. Anyway, that's the wave equation. Oops.